Good morning, everyone, and of course, the people online, right? And welcome to this session, this generally weekly session of the talks at the CoE Center of Excellence. We are honored to have Michele here. So let me give you a quick introduction on Michele Dougherty, who is a professor of space physics at Imperial College. Michele is leading unmanned exploratory missions to Saturn and Jupiter, and was the principal investigator for the magnetometer instrument on board the Cassini mission to Saturn, as well as being the principal investigator for the Jupiter Icy Moons Explorer, JUICE. Apparently, that's run by the European Space Agency and due to be launched this year sometime, or unless it's been done already, or early next year. Michele is the head of physics in the physics department at Imperial College. He's a fellow of the Royal Society, was awarded the Royal Astronomical Society Geophysics Gold Medal in 2017, and was awarded a CBE in the 2018 New Year's Honours List. He was awarded the Institute of Physics Richard Bracebrook Gold Medal and Prize. I suppose we can go on speaking about Michele. Okay, but whenever I see a picture of Saturn, it just drives me crazy. So, Michele, over to you.
Thank you very much. Thank you very much, Uncle. So, very nice to be here today. What I want to talk to you about is some of the work that my team and I have been doing on the different spacecraft missions that I'm involved in. And I'm going to start, first of all, by talking about the Cassini mission to Saturn. And this is my favorite picture of Saturn. The reason I like it so much is that it was essentially put together by about 1,000 images that the camera on board the Cassini spacecraft took over a long period of time. And it put them all together to give us this fantastic view of Saturn. So you can see Saturn itself, which is a gas giant. It doesn't have a solid surface. You can see the giant rings, the giant visible rings around Saturn. And then you can see a rather diffuse ring called the E ring. I will, for the people in the room, I'll be able to point it, but this is the diffuse E ring that you can see here. And one of the things I'm going to talk to you about today is a discovery that my team made of outgassing of water vapor that came from one of the moons. And those of you with really good eyesight can spot the moon in that ring, just in there, and you can also spot some of the outgassing. But I'll describe the observations that we made, how we made the discovery that we did. And last but not least, you can see the Earth. The Earth is peeping from behind one of the rings. So there we were with the spacecraft orbiting around Saturn, taking images of Saturn, and we could see the Earth in the far sort of distance. Put my glasses on so I can see how to change size. Here we go. Okay, so for a spacecraft mission as large as Cassini-Huygens was, you need to have international involvement in it. And so this view here shows you all the different countries that were involved in building the instruments, building the spacecraft. There were about 3,000 people who were involved in the mission itself. And the other reason I like to show this is it shows you a view of the spacecraft itself. So you can see there's a white umbrella-shaped object that's known as the high-gain antenna. And once a day, what would happen is the spacecraft would turn with the high-gain antenna facing at the Earth, and it would send the data down that we got back from the previous 24 hours. There's a very long boom that you can see sticking off from the side of the spacecraft. That's where I put my instrument. The instruments that we build at Imperial College measure the magnetic field. But what we want to do is measure the magnetic field in the environment, not due to the spacecraft. So we try and get ourselves as far away from the spacecraft. And you can see there's another almost umbrella-shaped object attached to the side of the spacecraft. That was the Huygens probe that was built by the European Space Agency, and that detached and traveled through the atmosphere of Titan and landed on the surface of Titan. And then the last thing to point out here is you can see that everything seems to be covered in a gold foil. That's a thermal blanket, and that helps keep that will help keep the instruments and the spacecraft at the kind of operating temperature that they need to be. So this view shows the Cassini spacecraft in the test chamber before the launch, and you can see how big it was, or yes, was, because it no longer exists anymore. But it was essentially 2 stories tall. You can see some people standing at the bottom. And again, you can see the high gain antenna, that white umbrella-shaped object. You cannot see the boom that my instrument was on, and the reason for that is that you can't launch a spacecraft with a large boom sticking off on the side of it. And so what we did is we folded the boom away into a canister and we deployed it after launch. And what we did in this test chamber is we made sure we put the spacecraft and the instruments in the conditions they would expect to see in space. So the different thermal gradients, we flew past Venus where the temperature was plus 40 degrees Celsius. Out at Saturn, it's minus 170 degrees Celsius. So we needed to make sure that it would operate in those extreme range of temperatures. So what I want to talk to you about today is, as I mentioned, one of the discoveries that we made with the Cassini instrument. And before I do that, I just wanted to set the scene a little bit. So what my instrument does is it measures the magnetic field. This shows you a view of the Earth, where if we could see what the magnetic field of the Earth looked like, it would look like those red field lines that you can see. So when you stand on the surface of the Earth, you've got a compass to point to the north pole of the field. And so that's what my instrument measures. Out in space, it's able to measure those field lines. One way of trying to visualize how the magnetic field is generated, it's generated in the interior of a body. And one way I like to think about it is you've got a piece of paper, you've got a dipole sort of magnet underneath that piece of paper, and you put iron filings on top of it. The iron filings are going to lie along the lines of force of the magnet. And that's one way of visualizing the field itself. In the interior of the Earth, there's a planetary dynamo that generates the field. And if we could see those field lines, that's what they would actually look like. The other thing I wanted to point out on this slide, and that's something I'm going to need you to visualize when we move on, is as a planet like the Earth or Saturn rotates once a day on its axis, those field lines are going to rotate at the same rate. And so if you're sitting on a moon, the field lines are going to be moving past you. And depending on how those field lines behave, you can tell what the moon is like, what the actual conditions of that moon are. So this here shows you a schematic of the Saturn system. Shows you Saturn and the visible rings, but it also shows you where all the various moons are in orbit around Saturn. And the moon that I want to talk to you about is Enceladus, which is within that diffuse E ring that I pointed out to you earlier. And something to keep in mind is that this diffuse E ring is the largest planetary ring in the solar system. And the particles within that ring are made up mainly of neutrons. So if we move on to the next slide, let me show you what we knew about Enceladus before we got there with Cassini. So this is 2 different pictures that were taken by the camera on board Cassini that show you what the surface of Enceladus looks like. We had 3 flybys of the spacecraft planned of Enceladus in early 2005. And there were 2 that took place quite early on in the year. They were quite distant. The first one was almost 1,300 kilometers away from the moon. The second one was 500 kilometers away. And then based on the observations that we made on those first 2 flybys, we were able to persuade the Cassini project to take us much closer on the third flyby. And I'll show you what that data looks like and why we thought it was interesting. But if you have a look at those 2 different images there, the thing that you'll notice is there's some cracks on the surface, but also there don't seem to be many craters on the surface. And that's quite a surprise, because in the previous slide, you've got Enceladus in its orbit, and inside of Enceladus you have Mimas, and outside of Enceladus you have Tethys. If you look at the surface of those 2 moons, they're covered in lots and lots of different craters. So something else is happening at Enceladus. Something is happening to make its surface much younger and crater-free. So before Cassini went there, we had long wondered whether Enceladus might somehow be the source of this diffuse E ring that Enceladus is sitting in, but we didn't know how that could actually be. And the other thing that we knew is there'd been a previous spacecraft, Voyager spacecraft, instrument on board that spacecraft was able to remotely sense what the surface was made of. It was made up mainly of water ice. So what we knew is the surface is water ice and the material in the E-ring is water ice. We didn't quite know how those two things connect. So we had two flybys of Enceladus. And you can only be a magnetometer person to get excited by this, but let me talk you through it. This is magnetometer data. This is 24 hours worth of data. And if you measure the magnetic field, it's a vector. So you measure three components of the field, and those first three panels are the different components of the magnetic field. The bottom panel is the magnetic field. And just beyond 330, you can see in the top and the third panel, there seems to be a sharp change in the magnetic field. Those of you with very good eyesight will see at round about that region, in the second and the fourth panel, there's a little pimple in the data. You can't see a huge amount of change because the magnetic field is quite strong there. And then the other thing to notice is on either side of that big disturbance, the field is very noisy. And we can use that noise in the data to help us understand what's actually generating noise. So if we put this into a different view, so what I've done here is now we're looking down on the North Pole of Enceladus. Saturn is way up to the top of the page, and the magnetic field lines and the plasma from Saturn are coming in from the left. So that's that plasma flow arrow that you can see. The line that we can see is the trajectory of the spacecraft. So that was the movement of the spacecraft. And overlain on top of that, I've put magnetic field vectors. But what I did first of all is I subtracted the magnetic field of Saturn away from the data. So all we're left with is the magnetic field due to Enceladus. And what you will see is it's almost as if Enceladus is a much bigger body than it looks. Something's stopping those field lines from actually penetrating down onto the surface. So it's almost as if they're being held upstream of the So with that in mind, and also the fact that we saw that large increase in wave activity, which was ion cyclotron wave activity, we were able to work out what ions were actually generating those waves, and it was an increase of water-cooled ions. So based on those two thoughts, and the fact that we saw similar signatures on two flybys separated by three months apart, we put this little video together to describe what it is we thought we would see. So first thing we're looking at is our eye is looking down on the North Pole of Saturn. We can see Saturn on the left of this group here. So you've got Saturn, which is the yellow ball, those gold rings are the visible rings of Saturn. The blue lines are the magnetic field lines of Saturn as they're orbiting around, as Saturn rotates on its axis. And the orange ball is Enceladus, that is moving around Saturn. Now, if Enceladus was a dead body, the magnetic field lines wouldn't see it at all. And they'd move straight through it, as you can see there. But instead, we seem to be seeing something different. Now we're looking sideways on at Enceladus. And the blue field line of Saturn is moving towards Enceladus, but instead of moving straight through it, it was being draped upstream. So something was stopping it from penetrating down onto the surface. One way you can do that is if you've got an atmosphere, just like we have on the Earth. So the Earth's atmosphere is ionized in the upper regions from interaction with solar ionization. And that ionized region forms plasma, and the magnetic field and plasma from the sun cannot penetrate through the Earth's atmosphere. So that's what protects it. If we had something like that at Enceladus, then the upper regions of the atmosphere would become ionized and would stop the magnetic field line. So what I did, or what the team did, is we put this little diagram together to show that we thought we were seeing a diffuse and extended atmosphere covering the entire surface of Enceladus. And then I went out to the Jet Propulsion Lab and I described to them, I showed them this and I showed them the data. And I said to them that we thought we were seeing an atmosphere of Enceladus. We thought it was a water vapor atmosphere, and we'd like to go really close on the third flyby. Took a bit of persuasion, because one of the things about the Cassini mission is we'd spent the 6 years it took us to get to Saturn, planning every single second of the observations that we going to take. And so if we changed the flyby, we would remove some observations from some of the teams. But eventually we agreed that it was worth doing. It was exciting enough that we should do it. And so what the Jet Propulsion Lab did is they changed the third flyby of Enceladus so that it was much closer. It was 173 kilometers above the South Pole. And this was completely fortuitous. We didn't know there was anything particular happening at the South Pole. So we came up from below Saturn and flew below the South Pole of Enceladus. And I must confess, 2 or 3 nights before that third flyby, imagine if they'd seen nothing at all. No one would ever have believed anything I said again. But luckily, they saw something. We saw something. And what we saw was really interesting. Instead of there being an atmosphere covering the entire moon, we had an outgassing of water vapor. It was like a cometary jet coming out from the South Pole of Enceladus. So we had this plume of water vapor coming out from the South Pole, and that's what was bending the field lines, and that's what was causing a huge increase of water group ions in the vicinity. So there were other data sets, of course, that were taken because we went so close. All the other instruments on the spacecraft were able to take data as well. So there are 2 different data sets that we're looking at here. The one in the top left is an image from the camera on board Cassini. And what you can see are cracks at the South Pole, blue colored cracks. And the team called them tiger stripes. In the bottom left-hand image is data from another instrument, which was an infrared instrument that was able to remotely sense the temperature of the surface. What they thought they would see is in the far left. They thought the hottest temperature would be near the equator where the solar radiation was strongest. And they did see it was hot there. But what they also found was that there was this hot spot right at the South Pole. And if you overlay the 2 data sets on top of each other, which is at the bottom right-hand image there, the hottest spot was right over one of these cracks in the surface. So the implication is that not only was water vapor leaking out, but internal heat was leaking out as well. This was a real surprise because Enceladus, I forgot to mention this earlier, Enceladus is quite small. It's got a diameter of 500 kilometers. And so you would have thought it had long since cooled down from when it first formed. So the fact that there was internal activity and internal heat leaking out meant that something was going on at Enceladus. We didn't quite understand. So we had internal heat, we had water vapor, which on subsequent flybys we found out was coming from a liquid water ocean underneath the surface. This here shows you another view from the camera, which turned back and looked at Enceladus, and it just shows you how vast the extent of the plume is. The different colors show you the different densities, and you might notice there seem to be different sources. So the cracks are opening or closing as Enceladus is orbiting around Saturn due to tidal forces. Because the orbit of Enceladus is not quite circular. So on some parts of the orbit, it's closer to Saturn, and others, that's what the tidal forces are. The other thing we discovered, and this was data taken by an instrument called the ion neutral mass spectrometer. And what that instrument did is it was almost, as it flew through the plume, it was almost able to taste what was in the plume. And this is what it found water vapor, but we knew that already because we had found water vapor signatures in our data. It found methane, it found carbon monoxide and carbon dioxide. But the most interesting thing of all is it's found organic material, both simple organic material and compound. And so now we had a place in the solar system where we had 3 of the 4 ingredients for life. We had liquid water, we had a heat source, we had organic material. The 4th thing we need to try and understand is how long those first 3 are there. They need to be there for a long period of time for something to happen. That's what we're not sure of at Enceladus. But ever since these flybys of Enceladus, there's now been a real focus on Enceladus itself. There are some plans for a future NASA mission to go to Enceladus. But it's also, and I think this is one of the most important outcomes, is it's made us realize that you don't need to focus close to the sun to be able to search for liquid water. search much further away from the sun and still find water, even though it's not liquid on the surface. I think this leads in quite nicely to this slide here. So I will come back to Cassini because at the end of the talk, I want to show you the end of the mission video. But before I do that, let me just talk a little bit about the upcoming missions. So I think one of the most important realizations in the last 30 years is the fact that you don't have to search close to the sun to be able to find water. You can go much further away from the sun. So this is quite a busy image, so let me talk you through it. And I'm just going to look at this screen because my eyes aren't good enough to see the details on that screen. So what we've got on the y-axis is we're looking at the mass of the star relative to the sun getting smaller as we go down. And on the bottom axis, we've got the radius of the orbit relative to the Earth. And so looking at this view here, we have our sun right in the middle, yellow sun. We've got Venus, we've got Mars, and then we've got the Earth. And previously, whenever you talk about searching for liquid water, you've always thought you need to find it on the surface. To do that, you need to be close to the sun. So there's been a real focus on Mars in particular. But what the Cassini observations in Enceladus have confirmed for us and some earlier observations from the NASA Galileo spacecraft in Jupiter have confirmed is that you can find liquid water underneath the surface. And so you move beyond the snow line, which is that yellow dotted line that you can see. And beyond the snow line means that if there is any liquid water on the surface, it's going to be ice. But you can find liquid water underneath the surface. And that's what has been found in the last 30 years. So Jupiter has got liquid water underneath the surfaces of 2 of its moons, 3 of its moons actually, Ganymede, Europa, and Callisto. And I'm going to talk a little bit about what the JUICE spacecraft is going to do. And then out at Saturn, we have got liquid water underneath the surface of Enceladus. I didn't have time to talk about it, but there's also liquid water underneath the surface as well. So there's now been a real focus away from having to search for potential habitability close to the sun or close to stars in other solar systems. So this is what our understanding of the internal structure of the 4 large Galilean moons at Jupiter was, following NASA's Galileo spacecraft. So the 4 large moons, as you can see, are Io in the top left. Io is a very strange moon in the sense that it's got volcanic activity on the surface, and it's sulfur volcanoes. So spacecraft try and keep as far away from Io as they can because the spacecraft and the instruments wouldn't last long in the environment of Io. Then you have Europa in the top right, and we know there's a liquid water ocean underneath the surface of Europa. We think it's quite close to the surface, and we're going to have a focus on trying to understand whether in the future we might actually be able to get under the surface at Europa. Bottom left is Ganymede, and Ganymede is the only moon in the solar system that has its own internal planetary field. So if you stood on the surface of Ganymede, your compass needle would point to the But we also are almost certain that there's a liquid water ocean. And in fact, the focus of JUICE is going to be at the end of the mission is to go into orbit around Ganymede, because to be able to understand an environment properly, you really need to orbit. Because you need to be able to separate temporal and spatial features from each other. And the only way you can really do that is if you go into orbit. And then bottom right is Callisto. Callisto again is different. You can see it doesn't have a solid core. So it isn't fully differentiated like the internal structure of the other 3 moons. And that's something we want to try and understand. What happened to Callisto in its formation that made its internal structure different? Okay, so this gives you an overview of the JUICE. So it began in 2008, actually. There was a joint study team between both ESA and NASA. NASA then pulled out because they said they couldn't afford to do it. And so ESA asked us to do a European-only study. We were then chosen as the first large class spacecraft to fly. And this is also the first orbiter of ICE. So the image that you can see there In the background is a view of Ganymede and its supposed internal structure. That's what we want to try and understand. Jupiter is in the background as well. See the magnetic field lines of Jupiter. And then you have a view of what the JUICE spacecraft looks like. And so you can see that we are using solar panels with JUICE. And in fact, I was sent an image, a picture overnight from the ESA project team. The spacecraft is in the test chamber at the moment, but the solar panels have been fitted. They've all been folded away. So the spacecraft is very close to being ready to be shipped to French Guiana. We've been delayed slightly. We've been delayed by 6 months. And to be frank, with all the chaos of COVID, the fact that the delay is only 6 months is pretty spectacular for my point. But as Abdul mentioned earlier, we're going to be launched early next year. I think it's May of next year. So I think, other than keeping the physics department going in lockdown, the thing I was most proud of was the fact that we were able to build a flight instrument in the midst of lockdown. I remember in March 2020, when everything shut down at Imperial College, the engineers took bits of the instrument home with them and started putting it together on their kitchen table because they couldn't do it any other way. We then were able to reopen our labs with a lot of social distancing in June of that year, but we were able to build the instrument in this time. So what you can see there are 3 different images there. The one in the top left shows the entire instrument on the table. So the black box is the electronics box, and that box goes into the main body of the spacecraft, so it's well protected from the radiation environment of Jupiter. And then there are 3 different instruments that go towards making up the full instrument suite. The one with the dome on it is the one that we build at Imperial College. And then we've got one which is built by colleagues in Germany and another built by colleagues in Austria. Bottom left shows that instrument on a vibration table. So what you need to do is you build different models of the instrument which get better and better as you get closer to launch. And you test those models and the electronics box on a vibration table to make sure they can survive the launch loads. And then the image on the right shows a large stick with a hard ball on the end that's about to hit the electronics box to see if it survives. Luckily it did, but it is rather nerve-wracking to have to watch this. Okay, so that shows a view of the spacecraft. The main reason I wanted to show this to you is it shows you how large the solar panels are. They're 76 meters square. And out at Jupiter, they will be giving us about 20 watts of power all the time. So that's how much power we will need to be able to use to operate all of the instruments. They will slowly degrade over time. We've also got other power sources on the spacecraft, but the main power source on the solar panel. And then the long boom that my instrument on is the one that's sticking down at the bottom of the spacecraft. But this is the first time that solar power is used as far out as Jupiter, and that's about as far out as we can go. The solar radiation at Saturn, for example, just isn't strong enough for solar power to. So there are 2 different areas that we're focusing on with my instrument at Jupiter. The first one I think is the most interesting for me, and that's I'm trying to resolve the internal structure of the different bodies. And I think the best way to describe it is that image in the top right there. What we want to try and understand is what the internal structure of this is. Is it ice from top to bottom? Is it ice and then some water and then more ice? Is it a slightly thinner ice crust and then water all the way to the bottom? And at Europa, we think is a very thin ice crust in the midst of the water all the way down. Now, what my instrument is able to do is, as it flies past a body which has liquid water in, if there is conductivity in that water, there's a salt content. If the body is moving through a changing magnetic field, an electrical current is produced, that electrical current generates a magnetic field, and my instrument can measure that. It's difficult to do, and I'll show you a view which gives me sleepless nights of what it is that we're trying to measure. But for me, this is the This is the most critical observation that we need to make so we can understand what the internal structure is. Because there'll be plans to send a spacecraft back to one of these moons in the future to try and get underneath the surface. And we need to know where the surface is thinnest so that we can. This is a more general science case, and that is really magnetometer measurements are crucial to understand a whole different type of plasma processes that take place. Bottom right, you can see the various moons embedded within the Jupiter system. These moons generate aurora. You can see the aurora at the north and south poles. You can see an image of the aurora in the bottom middle as well. And then top right, you've got Ganymede. That's got its own planetary field embedded in the magnetic field of Jupiter. So you've essentially got a mini magnetosphere inside the Jupiter one. And so it's a unique system. And by spending at least 3 years there, will allow us to much better understand. This is what keeps me awake at night. People say to you, if you wake up at 2 o'clock in the morning, what is it you think about? And this is what I think about. So I think we built the best instrument we've ever built. And we need to, because the kind of signatures we need to measure are hard. So there are three main signatures we're trying to measure. On the left-hand side, if there was nothing else going on at Ganymede, but there was the background magnetic field, those white lines that you can see. As it's moving through that field, the induction signature in the ocean makes those very small changes, those very small bends. We think it's about 2 nanotesla in a background magnetic field without a power. So that's the hardest thing we need to measure. But it's made complicated by the fact that that middle panel shows that Ganymede has its own internal planetary field, and that means there's a lot going on, and that we need to be able to model. And if we go into orbit, we will be able to do that. And then last but not least, on the right-hand side, everything's embedded in the magnetic field of Jupiter. That's changing all the time. And those red, that red ellipse and the red circle that you can see show you what the orbits are going to look like. So we'll start off by going into an elliptical orbit around Ganymede, and then at the end of the mission, we'll go into a circular orbit, hopefully about 200 kilometers above the surface. The way I like to describe it is like trying to find needles in a haystack, and the needles are changing shape and color all the time. I think we can do it, but I'm losing sleep about it at the moment. So let me move on to the last part of the talk. This was the end of the Cassini mission. So we spent 13 years orbiting around Saturn. 12 years in, it was clear to us that we were beginning to run out of fuel, and we needed to make a decision as to how we would end the mission. And one of the biggest surprises about the Cassini mission, other than the discovery we made in Enceladus, was the internal planetary dynamo at Saturn was very strange. The more we found out, the stranger it became. So planetary dynamo theory tells you that the way a magnetic field is generated in the interior of the planet is there's convection that takes place. So there's this bubbling, overturning motion. There's the rotation in the interior as well. And those all combine to generate the magnetic field you see outside. But planetary dynamo theory also tells you that there needs to be a tilt between the rotation axis of the planet and the dipole axis of the magnetic field. Without that tilt, you can't continue to generate the field. At Saturn, the more data we've got, the smaller the tilt became. And we just didn't understand that because it doesn't fit with planetary dynamo theory. So what we thought we'd do is we'd spend the last year of the mission getting ourselves into a situation where we could fly so close to Saturn that inside of the rings, just in case the rings were generating a magnetic field of their own. And we hope that would then allow us to find the tilt that we couldn't find. So this view here essentially shows you the last year of the mission. So we've got the orbit of Titan out at 20 planetary radii, which gives you an idea of the size we're looking at. The white orbits were known as the ring grazing orbits. So what we did is we used Titan to give us a gravity kick out of the equatorial plane to put us on these ring grazing orbits where the closest approach was just beyond the edge of the visible rings. And then after 6 months of that, we used Titan again to put us into those grand finale orbits, the blue orbits, where it took us inside the rings. And it was just above the atmosphere, Saturn, and then that final orbit is the orange orbit. Just to give you an idea about how close we got, that shows you a close-up view. We were about 3,000 kilometers above the town tops to start with. We got closer and closer. Because the end of the mission, we were going to burn up in the atmosphere of Saturn. Other reason I like to show this is it shows you clearly that the rings of Saturn aren't solid. If we could have seen the orbits, the spacecraft as it was going through, we would have been able to see through the rings. So back when they were first discovered by Cassini back in the 1800s, it was thought that they were really solid objects, but they essentially consist of countless individual particles, each in their own orbit that they formed this field. So that shows you an artist's impression of the spacecraft on its first dive between the rings. And it was very nerve-wracking because neither the spacecraft nor the instruments were designed to do this. In fact, for the magnetometer instrument, we had to recalibrate our instrument. We were moving into a measuring range when we were really close to Saturn that we hadn't seen since we flew past the Earth in 1998. So we had to persuade the project to allow us to roll the spacecraft around the closest approach so we could actually calibrate. But we also didn't know what was there. We thought it was empty, but we weren't sure. And so what was decided is that we would fly with the high gain antenna pointing in the direction of travel. So if there were any energetic dust particles, they would hit the antenna and hopefully not hit any of the instruments on the spacecraft. So I went out to the Jet Propulsion Lab for this first dive, and I remember bumping into the project manager who was really nervous. And he said to me, "I'm really nervous." I said, "Yeah, I'm nervous too." He said, "You should be more nervous than me because your instrument's on the boom. You're not protected by anything at all." So that made me feel even worse. And we sat there, it takes 40 minutes for data from the spacecraft to get back to the Earth. So it had dived and we weren't sure if it had survived, but it had survived. And in fact, there was nothing there. It was completely empty. There was no energetic dust particles at all. And so we did 22 of these dives, getting closer and closer all the time. And this just gives you an understanding of the planetary dynamo process that I was talking about earlier. The magnetic field lines you can see outside is what we are able to measure with the instruments that we build. And what it allows us to do is to get an understanding of what goes on inside. So I tried to show you there the planetary dynamo process, the rotation rather than the overturning. So, based on the observations from the end of the mission, we made some discoveries. There were new field line currents that we didn't expect to see. But I think for me, the most important and the most surprising discovery was that the tilt is so small, it's less than 0.00, lose track, 0.7 degrees. So it's tiny. And taking that at face value, it's telling you that we don't understand planetary dynamo. But in fact, what we think is happening is that the internal dynamo is as we expect, but that there's a secondary dynamo above the internal dynamo, which is actually masking the effect of the material. And so that's why every time we took more data and we got closer, it looked at the tilt using this mirror. So we're now working with the gravity team who are taking data as well to see if we can try and understand better the internal structure. So at the end of the mission, what happened was the spacecraft dived into the atmosphere. This shows you the equatorial region of Saturn. And this is data from an infrared instrument that's almost able to measure the internal heat that's leaking out. So the red is the internal heat and the black are clouds within the atmosphere. And that white ellipse there is where the spacecraft dove into the atmosphere. To put it into context, it was just above the equator in the northern hemisphere. This here shows a view in the mission control room after the end of the mission. It was really interesting. Towards the end of the mission, everyone was exhausted. We had a close flyby of Saturn every week and couldn't keep up. And so there was a part of me that was thinking it's going to be really good and it's going to be a relief when it's over. And then when it was over, I suddenly realized that 25 years of my life wasn't over, but I'd spent my life focusing on this, and now the real mission was over. We still had a lot of work to do, but the spacecraft wasn't there anymore. But I think for me, the most poignant moment was watching the screens in the top left of that image there. So those two data screens show that, so there's a background green trace, and then there's a single green peak. Those green peaks are telling us that the spacecraft is trying to And when we thought it was the end of the mission, that peak disappeared. We thought that was it, and then it came back again. The reason it came back again is because no one had told the Cassini spacecraft it was the end of the mission. And it had been trained to keep talking to the Earth. So it reoriented itself so we could keep sending data down to the Earth, and then it began to tumble, and there was nothing more. But let me show you. I know it starts straight away, so I won't move on to until I'm ready to start it. So this was a movie that NASA put together for what we planned to do for the end of the mission. It was put together a year before the end of the mission, and the spacecraft did everything that was expected of it. And I still can't believe that it survived all the way through. So let me move on. There's a movie with sound.
A lone explorer. On a mission to reveal the grandeur of Saturn, its rings and moons. After 20 years in space, NASA's Cassini spacecraft is running out of fuel. And so, to protect moons of Saturn that could have conditions suitable for life, a spectacular end has been planned for this long-lived traveler from Earth.
5, 4, 3, 2, 1. And liftoff of the Cassini spacecraft on a million-mile trek to Saturn. We have cleared the tower. Bridge program is in. Full program is in.
In 2004, following a 7-year journey through the solar system, Cassini arrived at Saturn.
Around to the SOI burn attitude or pointing position and light up the rockets.
The spacecraft carried a passenger, the European Huygens probe, the first human-made object to land on a world in the distant outer solar system.
Huygens arrival on Saturn's moon Titan.
For over a decade, Cassini has shared the wonders of Saturn and its family of icy moons, taking us to astounding worlds where methane rivers run to a methane sea, where jets of ice and gas are blasting material into space from a liquid water ocean that might harbor the ingredients for life. And Saturn, a giant world ruled by raging storms and delicate harmonies of gravity. Now, Cassini has one last daring assignment. Cassini's grand finale is a brand new adventure. 22 dives through the space between Saturn and its rings. As it repeatedly braves this unexplored region, Cassini seeks new insights about the origins of the rings and the nature of the planet's interior, closer to Saturn than ever before. On the final orbit, Cassini will plunge into Saturn, fighting to keep its antenna pointed at Earth as it transmits its farewell. In the skies of Saturn, the journey ends, as Cassini becomes part of the planet itself.
We'll take the first question from the audience here. Anyone? What?
So if the end of the mission is determined by when the probe runs out of fuel, how much fuel was on the probe at the start of the mission? Or what fraction of the probe's mass was fuel?
Probably about 20%. So for those online who might not have heard, the question was, what proportion of the mass on launch was fuel? It was about 20%. So we had two different fuel sources. We had normal sort of rocket fuel, but we also had radioisotopes on board. So that they were able to, most of the instruments ran with those. But the fuel we were running out of was the rocket fuel that would allow us to move the spacecraft. And what we didn't want to happen was for us to lose control of the spacecraft and have it crash land on one of the moons, where in the future we might find life. And then skeptics might turn to us and say, oh, but Cassini crashed, landed on the surface of the moon. And so you might have taken life there. You might want to ask me the question as to why we were able to land on time. But so that was why we wanted to plan the evolution. We could have just left it orbiting, but it might have crash landed on the Saturn. So we were able to land the Huygens probe on the surface of Titan because we put it through a planetary protection exercise beforehand. So you zap it and you kill any bugs before you put it on the space. My thought was Cassini had spent 20 years in space. Any bugs would have been dead by the time the end of the mission came, but we were being extra special.
Michele, do you measure any wind currents? Be able to make a similar to Mars? Did that have any influence?
Some of the instruments on the spacecraft were able to measure the wind speeds in the atmosphere of Saturn, and that was one of the things that allowed us to better interpret our data as well, because it turned out there was a field line current flowing between the edge of the D ring, and we were trying to work out how that happened. And it turns out that the winds in the two hemispheres are blowing at different speeds, and so as a result of that, there was an inconsistency in the plasma in the northern and southern hemisphere, and that generated current. So there were some instruments on board that were able to remotely sense. No, they're higher on Saturn because it's such a big system. It was, and I can't remember the number. I can find it out for you. But early on in the mission, actually, there was a windstorm in the northern hemisphere of Saturn. It almost looked a bit like the red spot on Jupiter. So there was some kind of upwind that took place in the atmosphere. And for a year, it was dispersed around Saturn. We saw it disperse over time. So the wind speeds are large, but I don't know what they are.
Was that calibrated?
No. If there'd been a probe, we would need to take that into account. But for us, calibration is really important because the offsets of the instrument change over time. So we need to know what the zero sort of level of the instrument is. Usually the way that you do that is you've got two instruments, one halfway down the boom and one at the end of the boom. The one at the end of the boom was built by the Jet Propulsion Lab and stopped operating a year after one. So the only way we could calibrate our instrument was to roll the whole spacecraft. And so that's what we had to do. We had to ask the project to allow us to roll the spacecraft. And in fact, at the end of the mission, I think I mentioned we went into the highest measuring range that we hadn't ever been in before. So we had to roll the spacecraft in that range because otherwise we couldn't have been able to take it. We could have taken the data, but we couldn't actually analyze it.
Just an observation. In terms of being away from the measuring, the probe is so sensitive to measure possibly some idea of ice or water.
So we were 10.8 meters away. But We also, there's a very stringent electromagnetic cleanliness program for spacecraft like Cassini and JUICE. And so, right from when the instrument teams first start building their instruments, they need to use non-magnetic parts. A model is put together so that they turn instruments on and you can tell what the different signal is. And also what has helped is if you've got two instruments, you can use the gradiometer technique and you can see how the spacecraft moves. So on Cassini, it was more difficult because we only had the one instrument, but we were able to calibrate. On JUICE, we've got three instruments. But again, the sort of cleanliness program as we're building instruments is critical. So we're doing final measurements at the moment, turning instruments on and off on the spacecraft to see what we can actually measure. So it's a fine line between instrument teams building exactly what they want and us saying, no, you can't do that because we won't be able to make
Why is the magnetic field strongest in the y direction, but the field strongest in the z direction?
Sorry. The actual labels on that plot, you spotted it, weren't correct. The top panel was the radial direction. The middle panel was the north-south theta directions, which is where it was strongest. And the third panel was the azimuth direction. I should have pointed that out.
So in that plot, when you're looking down on Enceladus,
What I've done is I've subtracted the magnetic field of Saturn away to that.
but the vectors are in the plane of Enceladus. Are they not pointing up and down the plane?
No, I've subtracted the Saturn field away and the dominant component of that. So all we were left with, we hope, was the sort of perturbation due to Enceladus.
Can I ask a quick question?
Of course.
So the instrument that's on Saturn, is that communicating with Earth?
Yes. Well, not anymore, but it was.
But what?
So yeah, what?
Well, Titan, sorry. Talk about the one at Titan.
Oh,
Sorry.
it ran out of power.
I mean, Carl Sagan goes on in one of his books about Titan and the possibility of Titan.
It ran out of power about 24 hours after it landed. But there's a NASA mission called Dragonfly, which is going to Titan. Which is going to have a drone on Titan. I mean, we've only just started having drones flying around on the Earth, but they're going to have a drone on Titan, and they're going to keep a spacecraft on the surface and be able to get data back. The Titan is weird. It's got liquid on the surface, but it's liquid methane. Not liquid. No, but we almost certainly is liquid.
So the
Because only liquid methane could be liquid with those kind of colors.
How long are the cracks on Enceladus? How long are they?
Oh. 15, 20 kilometers. But you can see deep sort of crevices going in, and you can see 2.5 kilometers
into the.
But what I find really interesting about those cracks is they open and close, and so you get different sources at different times. There was an image I didn't have time to show, but there was a close-up view of the cracks on the surface, and there's sort of stars showing you all the different sources which open and close over time, and that's due to the type of forces as the moon orbits around Saturn.
Were the cracks growing in length, or are they sort of fixed length?
We were there for such a short period of time when you consider the sort of lifetime of the solar system. There have been some models put together to try and work out how much longer Enceladus could continue to send water vapor out. They're talking about thousands of years. So maybe we're just lucky. Maybe we just have to be there while it was happening. But the E-ring has been there since the early 1800s. There were observations taken from the Earth, which they didn't know what it was, but looking back now,
Okay, I think. Oh, we still have. Okay.
Yes, you said something to the effect that in order to check habitation, you check in the organic material in the water, and they're supposed to be there long enough. So what?
Don't know. We don't know what that long enough is.
Okay.
So yeah, we think we need 4 things. And I've always been asked the question, how do we know it's like life on the Earth? Why does it need to be liquid water? And my answer always is, let's start with what we know. So liquid water, a heat source, organic material, and then those 3 things stable enough over a period of time for something to actually happen. So there was a really cute newspaper skit that I saw. So when I went out to the launch, I went to Cape Canaveral. So excited, the ground shook, and it was lovely. And then the following day, in the local newspaper was a little skit, and there was a picture of a little green person standing on the surface of Titan. And the next one showed the Huygens probe landing on this green person and squashing them to death. And then the third one had a sign behind it saying population equals 1. So you've got to be really careful. You need to know where you should go to be able to do the search. And so that's what we want to do. We want to find where the ice crusts are thinnest. So next time around, we try and get it.
I just have one more question. With the temperature of Enceladus, is it water vapor? Is that steam or water vapor? Because the temperatures were less than 100 Kelvin. So is it coming out just due to pressure?
We think it's coming out just due to pressure. Yeah. So yeah, you know, I couldn't see on that screen, but I remember now the hotspot was at 95 degrees Kelvin. And people look at you and think, hotspot, 95 degrees Kelvin, but out there, that's high.
David?
You said that the material of the rings was water ice.
Yes.
Is that a surprise? I thought it would be solid rock, you know, rather than water ice.
I think it was a surprise 30 years ago, but it was the Voyager spacecraft that spotted it was water ice. Yeah, it was a surprise, and so how did it? But maybe the moon that broke up that formed the rings, or the moons, were made up maybe of water ice, because we think Enceladus is made up of water ice. You know, there's a false color image of Saturn and its rings, where they colored the rings blue to show water ice. So if you ever see that, it's a bright red image of Saturn because of heat. And then it's a blue ring.
Jacob, you can ask your question.
Great presentation, Professor. I wanted to, my question is directed at is similar to one put by somebody there. The temperature on the surface of that moon, as you go towards the core, does it increase or decrease?
Sorry, I missed a bit about the tail.
Does the temperature increase or decrease as the distance decreases towards the moon? Now, as you get closer to the moon, does the temperature increase or decrease?
I don't know. I would think it would increase because I think vacuum is colder than solid, and so the view that I showed you of the surface of Enceladus with the different colors on it, that was a remote observation of the surface temperature.
Okay.
Does that answer your question?
I'm not sure if I understand. According to Professor Kara, the temperature at the surface, let's say it's 0. As you go down, it's going to go up. Is that what the professor is saying?
I missed part of your question, so I asked him to interpret it. Maybe he didn't interpret it right. Yeah, I wasn't sure of your question. Sorry. Ask your question again about how the temperature changes, please.
Okay, let me put it differently. Are there active volcanoes on that moon?
No, there aren't. No. So the hot spots that you saw in that surface image was of internal heat leaking out through the cracks, but they aren't volcanoes. It's it's water vapor escaping because of the difference in pressure.
Great, you've answered the question. You're
Okay.
actually saying as you go to the center of the moon, the temperature goes up. So are you
Yes.
saying the moon is losing some heat?
Yes, yes. And that's one of the real surprises, because we didn't think it was hot at all, because it should have cooled down a long time ago. Because it's so small, any heat that would have been generated when it first formed should have dissipated thousands and, well, millions of years ago. Because it hasn't, it means we know something different is going on there.
Okay, is some of that energy that is being lost to into space, is it electromagnetic?
No, the heat that's being lost into space is just being lost. The way that the magnetic field is changed is due to the fact that part of the water vapor plume is ionized, so it can't move through it. But also the magnetic field is picking up a lot of these water group ions.
Yeah, let me put it differently. If you had a spectrometer and you're on that moon,
Yeah.
will there be some frequencies that will pick up to indicate energy being released?
I don't know.